check if we're
Hello,
on
Angie.
YouTube now. Okay, good morning, everyone. So it's 8 o'clock in the morning. So thank you once again for joining us in the PAASE webinars. So this is our 20th lecture, not counting the lectures we had during the celebration of the PAASE anniversary. So this morning, we will talk about knowledge updating, decision making, and the search for truth through data. Our speaker is a professor of statistics at the University of South Carolina in Columbia, South Carolina. He is currently a program director in the Division of Mathematical Sciences of the Directorate of Mathematical and Physical Sciences at the National Science Foundation. He obtained his bachelor's and master's degrees in statistics from the University of the Philippines at Los Banos, and his his master's and PhD degrees in statistics from Florida State University. Prior to joining the University of South Carolina, he was a faculty member at UPLB, Bowling Green State University in Ohio, and the University of Michigan. He is an elected fellow of the American Statistical Association and an elected member of the International Statistical Institute. He is also currently serving as executive secretary of the Institute of Mathematical Statistics. His research is in mathematical statistics, foundational issues of statistical inference and decision making, stochastic modeling, and statistical analysis of time to event data, and in the reliability of complex systems. So that I am happy to welcome Professor Edsel Peña.
Okay, thank you, Kay. It's wonderful to give this talk. You know, Kay has been inviting me to give this talk, I think in May or June. And I was always finding reasons not to agree to it. So I said, because there's the PAASE conference that we had for 1 month in July to August. So I gave a talk to her for 15 minutes or 20 minutes. And I thought I was off the hook. I said, she will not invite me again. So I was very happy after the PAASE conference. And then I think a month ago, almost a month ago, it was my birthday. And Kay sent me an email and said, wishing me happy birthday. Okay. And of course, I was very happy that she greeted me, nice happy birthday. And then her next email was something like, will you now give a talk in this webinar? Now, if she only realized that whatever she would have requested me, I would have given to her during my birthday. She could have asked for $1,000 and I would have given it. At least she only asked me to give a talk, so it's a big bargain for me in this case. But it's my pleasure to give a talk, and I was mentioning earlier that it's always harder to present a talk for a general audience because I have to minimize certain text. But we'll see. Okay, so the title of my talk is a little bit high sounding. Okay, but I think this is very relevant these days. And first, I'd like to mention that I'm dedicating this talk to Professor C. Rao. He had turned 100 years old last week, and he is one of the pillars in the statistical community. I think he's one of the top 3 statisticians that are still alive. And he turned 100 years old last week, and I quote him here: all knowledge is in final analysis history, all sciences are in the abstract mathematics, and then all judgments are in the rational statistics. It is in a book that he wrote entitled Statistics in Truth. Okay, so and there he is. That is his famous book that he's holding. And when I was in Bowling Green, Ohio, he actually visited us during the time. So now, last month also I mentioned during the PAASE conference that it might be good for speakers to kind of tell a little bit about where they came from, especially since we are all in different fields. Some are engineers, some are chemists, physicists, and I thought I'll start that process then in some sense. So I put here an accidental statistician's continuing stochastic journey through life, but only in pictures. Okay, it is just going to be quick. And so this is where I came from. That island of Catanduanes that has that arrow there. That's a very small island in the Philippines. Actually, the arrow is pointing to where I actually came, and this is the old church there. You know, in the Philippines, it's a Catholic country, so we have many, many old churches from the Spanish colonization, and that's the church there. And then I remember the farmlands in my town, and you could see that the farmlands. It's a nice little town. Not very many things there, but it's a very rural town. So I wanted to show that to you. Okay, so I think I pressed the wrong thing. And this is the elementary school that I attended when I was in the Philippines. And this is the Panganiban Elementary School. It's an old one, and I think this is actually newer now. And then from the from that town, I went to Philippine Science High School. I was very lucky to get admitted here, so for my high school. And I think several people in the audience are also from Philippine Science, and this is the buildings that we have there. And from there, I went to Los Baños, UP Los Baños. So we have this beautiful campus in Los Baños. I think that was my ideal campus, and I enjoyed very much my stay in this university. And from Los Baños, I was there for 3 years to get my bachelor's, and I got my master's, and I also taught at Los Baños. And I think Sita Albacea, who is in the audience, was actually a student in one of my classes during that time. Yeah, it has been a long, long time. So, and from there, I went to Florida State University, that's in Tallahassee. So this is the entrance for the university, okay? And I had my first job in Bowling Green State University in Bowling Green, Ohio. This is actually the mathematics department. And that was me 2 years ago. I gave a talk there. So Marge took a picture of me in that building. I think my office is somewhere there. Yeah. And this is a tower in Bowling Green. I think Marcos Agustin, who is in the audience, was also in this university. Actually, he was a student there. Yeah, he was my student. Marcos was my student. Okay, so yeah, so that's Bowling Green. And then I visited Michigan for 2 years. We live in Ann Arbor, Michigan for 5 years while Marge was a postdoc. So this is the University of Michigan, one of the buildings there. It's a big university. And I went to the University of South Carolina. So this is where I am now. This is the what we call as the horseshoe. And every noontime when I could, I walk around here, and that's when I get a lot of thinking done. Okay, so and now I'll be in the National Science Foundation. So this is the National Science Foundation that's in Alexandria, Virginia. I have an office there, but I haven't been to my office because of COVID. So I'm still working from South Carolina, but somewhere there is my office. So this is the National Science Foundation. So that's my journey so far. And it's a random journey because you really never know where you will end up. And I put this there because for the younger people in the audience, just work hard. You never know where you will end up. Like C.R. Rao, for instance, he worked for, I think, 30 years in India. And then after the 30 years, he retired and then went to the US and he became professor at Pittsburgh and then Penn State. So, and then he published so many papers in India as well as in the US. So you never know. So just enjoy whatever you do, and then you'll never know where you will end up. I think that's the essence of my presented this part there. Now, before I start with talk per se, we now have to put a disclaimer. If you're working for the government, you have to put a disclaimer. And the disclaimer is that any opinions, findings, and conclusions or recommendations expressed in this talk are those of the speaker and do not necessarily reflect the views of the National Science Foundation. Of course, they support me, and then NIH also supported me, and then the University of South Carolina. So these are my acknowledgement for the support, but this is a disclaimer that we have to put in for every talk in paper that we publish if you are working for the government. And I think it's just the right thing to do, okay? Now, so what's all the fuss then? Okay, what's the talk about? And the talk about is about truth. Okay, If you see the newspapers, read the newspapers, we're always talking about what's the truth of something. So it's a big, big thing, but we never know what it is or the intricacies of finding the truth. Okay, and I would say here that one of the reasons of our existence is the search for truth. Of course, just surviving, but maybe the more important reason is that we want to explain things, we want to gain knowledge, and so on. It's kind of our scientists' creeds, engineers' creed, in anybody actually to understand into the truth in nothing but the truth. Okay, and there's a biblical saying that says, "And you shall know the truth, and the truth shall make you free." Okay, actually, I think that's in the CIA building and so on. Now, why do we want that? Because with good knowledge of the truth, we could make correct decisions. And decisions are important for our everyday living. Should you wear a mask? Should we use the hydroxychloroquine for COVID-19? All of those are important questions that we have to answer. And with truth in understanding, man makes progress. But of course, if you use that knowledge properly, sometimes you also use it in a poor way, and then disaster happens. It could improve the quality of our lives. We get better food, effective medicine, and living comforts. Now, last week, there was a big event in mathematics. Professor Sir Martin Hayter, he's a professor at Imperial College in London. He won $3 million as a breakthrough in mathematics award. The Zuckerbergs of Facebook, and then Breen of Google, and I think Milner, an Israeli guy, these are all billionaires. They set up this fund, and then they award $3 million to the winner of this prize every year. And Martin Hayter won it last week, and he's being honored for contributions to stochastic analysis and stochastic partial differential equations. A very complicated subject because it deals with randomness. But in randomness, there's also structure, and that was what he was trying to do in his research. But the reason I put it here is because of this quotation from him. Mathematics is truth. Once you discover something in mathematics, it applies to all eternity. So mathematics has a different sense in that way, because if you discover a theorem, if it is a correct theorem, nothing could disprove it. It will be true forever, whether we are all gone and so on and so forth. It might even be hold true in other parts of the universe in that case. So this is a very important quotation, and I put it there because of the idea of truth, absolute truth in that situation. Now, you could actually classify truths, and one of the classification of truths is what we call as deterministic truth or absolute truth. Okay, and an example of a deterministic or absolute truth is that the square root of 2 is an irrational number. Now, some of you might have read about the Pythagoreans. Okay, these are the Greek scholars during long time ago, and they thought that every number could be expressed as the ratio of 2 integers. Okay, so that because they thought that the integers are the building blocks, and every other number is the ratio of 2 numbers. Those ratios are what we call as rational numbers. Now, you could imagine the situation during that time when one of their students named Hippasus came one morning, say, and said, "Oh, I'm able to show that the square root of 2 is not the ratio of 2 integers." Okay, and he is able to prove that you couldn't actually express the square root of 2 as the ratio of 2 integers. Now, this was a big event for the Pythagoreans because everything crumbles for them because they thought that every number is actually the ratio of 2 integers. So that's why I call this as a deadly truth, because I think the Pythagorean elders gathered and say, what are we going to do? And so what they simply did is they tied Hippasus to a stone, and then they threw him out in the lake, in giant lake, and never to be seen again because they couldn't reveal that the square root of 2 is actually not a fraction. Okay, but it turns out, of course, that fact that the square root of 2 is an irrational number came out to be a very important one, because that led to the discovery of calculus, limit operations, and so on and so forth. So it was deadly in the beginning, but it was actually the engine of progress later on. So but that is an absolute truth, and that's a mathematical truth in that case. The value of the speed of light in the theory of relativity, for instance, is also an absolute truth. It's denoted by c. Okay, of course, the value that we had for this is an approximation, but we have an absolute truth for the speed of light in a vacuum. Another kind of truth is, let's say that you have a defendant. A defendant is accused of murdering somebody. Now, either the defendant is guilty or the defendant is not guilty. There's an absolute truth to the state of that defendant. We want to discover that, of course. So that's again an absolute truth in that case. Whether hydroxychloroquine is better than a placebo is also for treating COVID-19 patients, at least say for at least 6 years old. That's another absolute truth that you would like to discover. And putting it in contemporary times, you could say whether the president actually uttered the words "losers in suckers" about military people. It's either true or it is false, but only one of them is going to be true. That's again an absolute truth, and we would like to discover what the truth is. Whether there are extensive natural gas reserves in the South China Sea. Okay, so that's again a truth that we would like to know, because if there is, then maybe the different countries in Southeast Asia are very interested in controlling the South China Sea. Okay, so those are examples of what we would call as absolute truths. But at the same time, you also have what you call as probabilistic truths, okay? So a very simple example of this is if I have a coin and I say this coin is fair. What do we mean by fair? Well, it simply means to us that if you flip this coin many, many times, then 50% of the time it will land up heads, and then 50% of the time it will land up tails. So this is kind of the idea of a fair distribution for this coin. While if it is a biased coin, then you will have different proportion for the heads and then for the tails. Or you could say, what is a fair die? A fair die, again, is the situation where if you keep repeating throwing this die, you will get equal proportion of the occurrences of 1 to up to 6, and then you will say it is a biased die if you have a different proportion than 1/6 for this outcome. So here, these are examples, simple examples, but you could certainly relate it to situations in society where you might say, is it the case that Black defendants, for instance, in America, are getting worse treatment than, say, other race? So that you could convert it in this type of problem. But in our studies, we typically just connote this or denote this in terms of dice or coins. They could represent something much more. Okay, so that's the idea. And in this situation where you have probabilistic truths, you represent them in terms of what we call as probability distributions. Okay. Now, other ones are deaths. Okay, so you could ask, what is the number of deaths due to COVID-19 by the end of this year? We do not know that. That's a random thing, but you could describe it according to some distribution. You might say that it might have an average number of 350,000, but there's a variation that is represented by this density, for instance. Okay, or you could ask, what will be the temperature at Ninoy Aquino International Airport on noontime at January 1, 2021. Now, it's a random thing at this point, but maybe you could describe it according to some probability distribution. So again, these are probabilistic truths. Okay, and other examples might be whether a gene is associated with a phenotype or medical intervention, the impact of medical intervention on the lifetime of patient. That's also thanks. And to me, I'm a chess player. So when I sit in front of my opponent, my mind says, what is his first move? Because there are basically several possibilities. And again, that's a probabilistic truth in that situation because it's a distribution that you are considering. Okay. Now, how do we represent our knowledge of truth? Okay. Again, unless you can prove things mathematically, or I put here, unless a dependent confesses his crime or non-crime, okay, you could never be 100% certain about your knowledge of the truth. So what usually happens is that our knowledge of the truth is represented by a probability distribution. Okay, just like the representation of a probabilistic truth. Okay, so however, our knowledge of it is typically through a probability distribution over the space of possible truths. So if I give you a coin, for instance, I could ask you, what is your knowledge about whether this coin is fair or not? And then you look at the coin, you say, oh, it looks symmetric, okay? But then you might say, I couldn't be certain that that's really 100% fair. So you might say maybe 95% fair. It may be 5% not fair. So in that situation, you put a probability distribution to the two possibilities in that case. Or if I ask you about your knowledge about the temperature at the airport on January 1 noontime, you might say that it has a normal distribution with a certain mean in a certain standard deviation. So that could be your knowledge of the truth in that situation. And what you would like to do is to try to update that knowledge. Your initial knowledge will be maybe imprecise. So what you would like to do is to try to update that through the observation of data. Okay, and that's where I am headed here. But before that, I just wanted to mention that when you're dealing with knowledge of truth, or when you're dealing with probabilistic truths, then you have to use the language of probability. Probability is the language of uncertainty. Okay, so and a very simple situation, of course, is flipping a coin. It could be heads or tails, and then there's a certain probability for heads or tails. Okay, or you could have more complicated random experiments. It leads to events like A and B here. Those are subsets of what we call a sample space. And then you can measure the degree of certainty or uncertainty associated with these events through this notion of probability, which are numbers between 0 and 1. The whole event, of course, the whole sample space has probability 1, while an empty event has probability 0. And if you have two events that do not intersect, you call them mutually exclusive, then you should be able to add up their probabilities to obtain the probability of either one of them occurring. Now, there's of course a question here of how you come up with the probabilities, okay, or how do you interpret them? One way to interpret them is through the frequentist approach, where you keep repeating the experiment, and then you observe the proportion of times that an event is occurring. If you keep repeating that and you look at that proportion, it's going to stabilize. In that stabilizing value is the probability. But there are certain situations where you couldn't repeat the experiment. One example, for instance, is the outcome of the election this coming November. There's only one experiment that will happen on November 3. But I could ask you, what do you think is the probability that Biden is going to beat Trump? Then the probability that you will give me, that is what you call a subjective probability. But then if I ask another person about that probability, he might end up with a different probability. That's why you call it a subjective, because two different people could have two different assessments of that probability of that event. But however you assign the probabilities of events in a sample space, they must satisfy certain mathematical properties. And those are actually what we call as the Kolmogorov axioms properties. But that's the technical aspect there. Now, when you have an experiment, you could convert its outcome here to a real number. And then that is what you call as a random variable. And then that will induce also a probability of the possible values of this variable, okay? And usually, you could then say, what's the probability that this function takes value in C? Then you should be able to integrate a certain function over that C, which is the area under that curve, to give you the probability. And then this function, f sub x, is what you call as the probability density function. Or if you have a discrete case, that will be called the probability mass function. But the Tudor probability is very interesting, okay? Very difficult subject for a lot of students, but it's a beautiful subject and it's a very, very rich subject. For those of you who are not in mathematics, you should read a little bit about probability because it's a very nice subject. Okay. Now, just to formalize a little bit, random variables are usually called features now in machine learning or data science. Instead of calling them random variables, we typically would call them now as features. Okay. And you could have a random vector where you have two of them, or you could have three random variables and so on and so forth. The density has this interpretation that if you multiply a density by dx, then that's the approximate probability that the variable will be between these two numbers. And then you could also have the joint probability, same interpretation. And then you have a mean, you have a variance and a standard deviation, and then you could have a covariance, which is the measure of the degree of linear association between two variables, in this case, two functions of random variables. Now, the thing is to think about this as in pictures. So these are what you call as densities. Okay, these are actually what you call as Gaussian or normal densities. This has a certain mean here, I think 40 in a certain standard deviation. The standard deviation is a measure of variability. And then the other one has a mean 40 also, but a larger standard deviation. And then the red one has a different mean. So that's how it affects the shape of the distribution. You could also have skew distributions, like if you're dealing with lifetimes and so on and so forth, then you have a non-symmetric type of distribution and you get right skewed things there. Or you could have joint distributions. So this is a bivariate distribution. That's actually what you call as a bivariate normal. It's like a mountain when you're dealing with two random variables. Of course, we couldn't picture densities for three random variables anymore because that will be in four-dimensional space. We could simply imagine that in that case, but the principles are the same in that situation. Now, what are the ways of seeking truth from data? Okay, there are basically several. One of them is what we call significance testing. Okay, and the idea in significance testing is that you have a model, you get data, and you say, is this data consistent with the model? Is it confirming that model? Okay, that's what you call significance testing. And this was developed by Carl Pearson and Ronald Fisher in the early 1900s. Okay, you also have what you call as hypothesis testing approach that were developed by Jerzy Neiman, Egon Pearson. Here, what you have is you have two possibilities, and then you would like to decide based on the data which of these two possibilities is correct. Okay, of course, you could never be certain which one will be correct, but that's what you try to do. And then you have what you call as decision theory, developed by Abraham Wald in the 1940s to 1950s. And this is the setting that I'll show you a little bit because this is the more general setting that includes both of these. And of course, you also have what we call as the Bayesian approach, which I'll also mention later on. And this has gained a lot of popularity recently because of computing technology. Okay, it requires a lot of computations. So with the advent of high-speed computers and very powerful computers, we could now implement the Bayesian approach. And in fact, as I will mention later, the Bayesian approach is the right way to do updating, sequential updating. Okay. Now, nowadays, though, there's also another approach, which we call as the algorithmic approach. And a lot of machine learning, artificial intelligence, or modern data science methods are using this algorithmic approach instead of the more classical approach. These are more computing intensive type of procedures. Neural nets, deep learning, for instance, or SPM, they are all using this algorithmic approach in that case. And you could kind of think about the algorithmic approach as a non-parametric approach to seeking truth or knowledge using data. I will not emphasize this too much, that's for another talk, but I'll mention a little bit more about the earlier ones, okay? Now, these are other data-driven decision-making activities that we get involved in, okay? So you have what you call as A/B testing. This is very popular in Google, for instance, or Facebook. You have precision or personalized medicine, which is trying to determine the intervention that will be done on the basis of the data for each patient. So it's kind of precision medicine or personalized medicine. You could have prediction in forecasting. This could be, say, in the stock market or climate or weather prediction, classification discrimination, clustering into communities. I think I saw Xiwen Shen. He was my former student at USC here, and he's in New York now. But his thesis was dealing with clustering into communities in what you call as network models. You have recommender systems. If you open Facebook, let's say that you have been searching for maybe a gardening tool. Okay, you wanted to buy a gardening tool. Then when you next time you look at your Facebook account, suddenly there are pictures there of gardening tools. And you might say, how the heck are they doing that? That's all being done by these recommender systems. Okay, they're trying to make you buy a particular product, and the theory behind that or the technology behind that is these recommender systems, and these are all based on data. Segmentation in business, the engineers uses control systems in automated systems. And a lot of these are based on the theories that we have in statistics or data science, machine learning, or artificial intelligence. Now, where do we find data? Okay. Now, you could find data in many ways. It could be from scientific or engineering experiments. I think Raymond and Kay and Angeline, they do a lot of scientific experiments or engineering experiments. Some of them are quite expensive, but the purpose is to get data. You could have designed scientific experiments or randomized clinical trials. Of course, for those of you who are following the COVID-19 vaccine trials, this has been mentioned a lot because the randomized clinical trials are the gold standard, but sometimes it might not be possible to do that. But that's what we would like to do to actually determine if one treatment is better, say, than the placebo. Okay, you could obtain data from surveys. It could be political, social, or economic. You could obtain it from opinion polls, government monitoring, observational studies if you couldn't do these controlled experiments, high throughput studies like my wife Marge, they do a lot of omics studies, microarrays. So they have this technology that produces so much data because they examine every gene, for instance. Or you could obtain data from satellite and GPS systems or automated data gathering systems, which usually generate big data. Think about a nice Tesla car that is automated. Okay, how do you do that? There are sensors that's gathering so much data every millisecond, maybe, and then that data is fed into the algorithms, and then the algorithm decides whether to turn, to stop, or whatever. Okay, those are automated data gathering systems, and then the technology behind that is all about these types of situations. Well, but there are many possibilities. But again, you need to be careful about the type of data that you are gathering, because you could have data that are biased. You could have data that are too noisy. And if that's the situation, they might as well be useless for your purposes, or it will lead you to the wrong conclusion. So there you need to be careful also. Okay, you always need to examine that. And then there are many data types or structures. You could have the usual vector of numbers that a lot of us have seen, or characters or objects. You could have arrays of numbers like matrices, okay? Or you could have tensor data. Tensor data is kind of a higher dimensional matrix, okay? But nowadays, these are getting considered in the statistical literature too. You could have many observations, okay? But a small number of features, okay? You would say large and small p. Or you could have a large number of features, like maybe you have 23,000 genes, but you have only examined maybe 1,000 patients. In that situation, you would say that you have a large P or very large P, a small or moderate sample size. Okay, this happens a lot now in the biological or the medical sciences. You could have time series data or spatial data in ecology or in a stock market. You could have this type of data. You could have network data now, okay? So as I said earlier, my former student, work on this network data. Or you could have survival in time to event data. This topic has been my specialty in my research. I've done a lot of work on survival in event time data, and We are still working on this, and we have some new models that we're going to introduce on event time data, recurrent data, longitudinal marker, and then time to event data simultaneously. Okay, so now you could have several concrete problems that might be of interest to you where you need to use data. So, I put here a few. So you could ask, who will win the electoral college vote in the US presidential election this November? How do you go through that? How would you decide on that if you are being asked to determine that? Okay, and that's where opinion polling comes in. Of course, it's actually much more complicated in the US because it's through the electoral college. Okay, so as compared to the Philippines, where it's just a majority vote. Okay, you could, for instance, ask maybe Joel Coelho is very much interested in this. What is the proportion of the population of voters in the Philippines with a favorable opinion of science? Okay, apparently it's quite low. It's also in the US. I think from what I've read, it's only about 35% that has a positive opinion of science. We need to change that. Okay, so you could ask the question, is hydroxychloroquine better than a placebo in treating COVID-19 patients? That's a problem that we have these days. How do you decide on that? Again, that requires data. On the average, do college graduates earn at least $20,000 per year over non-college graduates? Or is that 20,000 too high? Or maybe they're the same. So how do you decide on that? That requires data. Or a geologist might ask, what is the probability of a major earthquake in the Philippines next year? Now, that's a more complicated problem, okay? But how do you do that? Then again, you could get data. What is the best prediction of the number of COVID-19 deaths by the end of 2020 in the US? I'll mention a little bit about this in the end if I have time, okay? So those are concrete problems that requires data to answer. Okay, and this is the type of problems that we have, but you could have other problems. Whatever area you are doing, you could have lots of problems that might be of interest to you, but they all require data. Now, so how do we do this, okay? So on this slide, I put a kind of a schematic. I'm always impressed by the engineers when they give talks. They always have these nice pictures in flow charts, and I promised Kay that I'm going to sketch some pictures here too. But this is how I review that, okay? The starting point is that you have this truth space, okay? This is where the truth resides. There are many possibilities. I call them as theta, but that's a big question mark. You want to discover the truth. Sometimes you might be trying to discover a picture of this truth, so a function of theta. So this is the one that you really want to discover, but there's an underlying truth that you want to discover tau. That could be the mean, or that could be the variance, or it could be the probability, or it could be something else, okay? But you want to discover this, okay? Now you have prior knowledge about the truth that is given by this distribution, which we call as pi theta. That's what you call as the prior knowledge. That is your subjective knowledge of what you think the truth is, okay? So it's a probabilistic one, okay? Now, what you would like to do is to choose an action. Okay, you have another set here. This is what you call as the action space. This is the choices for you. And what you would like to do is to choose an action here that will try to coincide with what the truth is. So when you have a truth, when you have an action, there's a loss that you will incur. Usually, if the A here coincides with the tau, then you don't have any loss. But if the A is different from the tau, then you will incur a loss, okay? So the problem is to choose an A that will be close to the truth, whatever is the truth. But there's a measure of the discrepancy of your action with what the truth is, okay? That's what you call as the loss. Now, but you want to use data to make that decision. So what do? You do an experiment, or you do a study, or you observe data. The data is going to be denoted by X. That could be a complicated data, but I simply denote that by X. And it takes values in what you call as the sample space or the data space. And you will see one of these values of this observable, okay? And based on this observed value, you then want to use that to choose the action that you'll be using, Now, you choose that action by having what you call as a decision function, okay? So that will take this data into this function that will then give you the action that you are going to choose, okay? And this delta x is what we are trying to do. As a mathematical statistician, what we want to discover is what are the deltas that are good for making decisions. Okay, this is our goal, to try to determine that. Now, on this part here, you notice that I also put x given theta has a density fx theta. Now, this is very important because what this indicates to you is that the experiment that you are doing is informative for theta in the sense that the data that you are going to see contains information about the truth. Because if the data that you're going to see doesn't contain information about the truth, then you have just wasted your time. You will not be using an informative data to choose your action. It's just like you are guessing. Okay, so that's the idea. So the truth, you wanted this, you want to choose an action through a decision function that uses the data, and maybe you will use your prior information, prior knowledge. So that's the kind of picture of the decision-making process in that situation. And the question is, what is the best delta to utilize to decide to choose the action? Now, this one is for truth discovery, where you are interested in the truth theta or the tahoe, but you could also have the prediction problem. In the prediction problem, it's very similar to the earlier one, except that you will be interested in another variable, which I called y here, that depends on the truth. Okay, so the data will govern the outcome of y, but that's random. And then what you would like to do is to predict that y. Again, you wanted to choose an action that will tend to be close to this y, and the measure of the degree of closeness is going to be given by some loss function. Okay, and which is this. And again, what you would like to do is that you will see a data through this experiment, using an informative experiment, and then you would like to use this data that you see to put into this decision function to choose the action. Again, the question is, what should be the delta that you'll be using? This is the problem that we mathematical statisticians try to figure out, okay? And we are looking for the best one or for good ones in that situation, okay? So that's the basic picture if you want to put it in a picture form. Okay, now you might ask, why do we need to do the best methods, okay? So let me drink my coffee here. Why do we need to have good methods or best methods? Now, if you're using the best decision function here or here, okay, then what it will do is that it will reduce the cost or the resource requirements, okay? So instead of spending $10 million, maybe you'll be spending $5 million, okay? Or instead of using, requiring 100 people, maybe you're only using 50 people for the same outcome, okay? So you could have that reduction in number of units. Like if you're doing mice experiments, then instead of using 200 mice, you might only be using 100 mice if you're using good methods. You are able to make precise and accurate conclusions in decisions in a timely fashion. Okay, imagine, for instance, trying to accelerate COVID-19 trials. If you have good methods, then you might be able to shorten that trial. So to be able to get to us, it's good for the environment. And we always say that we want the loudest bang for the buck. Okay, so and that's efficiency. You want to be efficient. And I put here, which one would you prefer? Would you prefer a car that takes 4 hours to reach your destination and consumes 4 gallons of gasoline? Or would you like a car that takes 2 hours to reach the destination and consumes 2 gallons of gasoline? Of course, you would like this one because you conserve a lot of things. And that's the reason why we would like to choose the best delta. And that's the problem that we have in mathematical statistics. What is the best decision function that we could utilize, okay? Now, let me just go back a little bit to that problem of informative experiments, okay? I said earlier that the experiment is informative about the truth theta if the observable x that you have has a distribution that depends on theta. Okay, that's the basic definition of an informative experiment in a stochastic or probabilistic sense. Now, you could actually measure the amount of information in this x about theta by using the feature information. In the Fisher information is simply the variance of the derivative of the logarithm of the density function. Okay, Fisher is one of the pillars in statistics, and he developed this information in the 1920s. Okay, you could also use other information like Shannon's information or Kolbach-Klibler information. You could also have those, but this is a measure of the amount of information, and the larger this is, the more information that observable has about this parameter theta. Now, here's a very simple example. If I flip a coin, a biased coin, okay, with probability of head being theta, okay, then I denote 0 if tail, and then 1 if head. The probability mass function for this x is given by what we call as the Bernoulli mass function. It is theta if it is 1, and then 1 minus theta if it is 0. So that's what you call as the Bernoulli distribution. It's the simplest distribution, discrete distribution that you could have aside from the trivial one. Now, you could calculate the Fisher information for this by following this. And it turns out that this Fisher information, based on one observation, is 1 over theta times 1 minus theta. That is 1 over the variance of x. The larger the variance, the less information. The smaller the variance, the more information. And the least information for this is obtained if you have a fair coin. Because if you have a fair coin, then it's the hardest to predict in that situation. While if the coin has 2 heads, it's so simple. You just flip it once, you know exactly that's going to be head in that situation. So the information there is infinite actually. But this is a measure of what you call as information. Now, I wanted to mention something that's very interesting about this, okay? And I say, but beware of noise on information. So remember earlier, I'm going to flip a coin with probability theta of head. Now, suppose that aside from flipping that coin, I flip also a fair coin. Okay, so I flip that biased coin, and then I flip a fair coin. What I'm going to do then is that if the outcome of this flip of the fair coin is a head, I will report the value of that first flip. If the outcome of the flip of the fair coin is a tail, though, I will report to you the opposite of the outcome of the biased coin. I'm going to call X star to be the resulting observable. Okay? Now, I could ask you, what is the information contained about theta from X star? That's the contaminated observation. And it turns out that when you do this, X star has completely no information about theta. Okay, so the noise, the process of that I did here completely eliminated the information about theta. And I put here kind of a question for you. What is the relevance of this noise contamination in our contemporary times? Okay, where say Dr. Fauci would say masks are important, and then say President Trump says, well, you know, it doesn't really matter. It's like something like this, and so information or propaganda sometimes could completely annihilate the information that is contained in a otherwise informative data point. Okay, so what I think about that, but this is just an illustration of the essence of information. Not every observation that you're going to see is informative. And we see that a lot these days with fake news. One of the things that we need to do is to try to determine what information something has. But that's a complicated thing to do, okay? So, but I just wanted to do that. Now, in the setting that I was considering earlier, okay, here or here, we could define 2 important functions, okay? So, and these are the risk function, okay, which I denote by R theta for a decision function delta. And that risk function is nothing but the average loss you incurred by using a decision function delta. And that's the integral, that's the averaging out with respect to this density. And then if you take the average value of this risk with respect to the prior knowledge that you have, that is what you call as the base risk. So the risk function at a given theta for a given delta is the average loss that you incur because the X there is a random thing, okay? So that's the average one. You want that to be small as much as possible. While the base risk you take into consideration here the prior, and then you average out this, and then that will give you the base risk. Okay, so risk function is the average loss, and then the base risk is the average risk with respect to that prior knowledge. Okay, these are two functions that are important to us. Okay, now just to give you an example here. Okay, let's say that we're trying to determine whether hydroxyl chloroquine is effective or not. Then you will have two statements here. One of them is I denote that by H of 0, that it is not effective. Maybe that's the status quo, okay, relative to the placebo. And then H of 1, which called as the alternative, is that it is effective relative to placebo. So the truth space then is going to be theta 0, H of 0 is true. In theta 1, H of 1 is true. The action space from which you're going to choose your action will contain two elements. A0 decide for H of 0, or A1 decides for H1. So you're trying to decide which one you're going to choose here. But of course, you'll never know which one is the real truth here, but you want to decide that. Now, in this situation, you could have the following loss function. If theta 0 in A0 coincides, then the loss is 0, or if theta 1 in A1. While if you get theta 0 in A1 is your action, then you get a loss. This could be something else, by the way. They need not be equal. Or if the truth is theta 0 and you take the action A1, you will also incur a loss. But here I simply put loss of 1. So it's either 0 loss or it is a loss of 1. But you could actually put C0 here, and then you could put C1 if you wanted to have different consequences for the two types of errors. Okay. Now, in this situation, you could have two types of errors. One of them is that you decide for A1 when the truth is theta 0, or the other one is that you decide for A0 when the truth is actually theta 1. And those are the ones that leads to a loss, the positive loss in that situation. And I could ask you here, in your opinion, which one is a more serious type of error? Is the error of declaring that hydroxyl chloroquine is effective when it is not serious? Or is the error of declaring that hydroxyl chloroquine is not effective when in fact it is effective? Which one is a more serious error? Of course, it's possible that you also have side effects in this hydroxyl chloroquine. But that's a decision problem that could be of interest. And in August 6th, there was actually a paper that came out. This is kind of a controversial paper because the way they concluded it from a statistical point of view was kind of erroneous, but this was a paper that came out in August 6th. Lots of citations immediately for this particular paper, okay? But the essence of that paper is that you have the placebo group, and then you will have the hydroxyl chloroquine group. What they did is they subjected M subjects, okay, to this group, okay, randomized, of course, and then they observe if it was successful or if it was a failure. And then X represents the total number of successes in this group. And then for the other group, the hydroxyl chloroquine, they subjected N people, I think about 800 people each, and then they also observed if success or failure. And they denoted by Y the number of successes in that group. Okay, so the data that you are seeing will be X and then Y. The data space then will be the product space of 0 to M and then 0 to N. That's your data space. And if you denote by P1 the success rate for the placebo group, and by P2 the rate for H of C, then these are the probability functions. It's binomial probability function, binomial probability function. And then you are then trying to decide if P1 is at least equal to P2. So that means that hydroxyl chloroquine is not effective, or if P1 is smaller than or equal to P2. This is the case where the hydroxyl chloroquine group is better in that case. Okay, you're trying to decide between these two, and then the data that you will see is the X and the Y. And that's the basis of this particular paper, for instance, okay? And you will usually have prior knowledge about P1 and P2. In there, you will typically put independent priors on P1 and P2, okay? So And when you look at the setting that we have, you will then have a decision function, and that will take values A0 or A1. Okay, A0 will be choose that a hydroxyl chloroquine is not effective, and then A1 is that hydroxyl chloroquine is effective. You're trying to choose between this on the basis of this data. If you look at the risk function, it's actually quite simple, because the risk function for a given decision function is simply the probability of a type 1 error under that decision function. If P1 is greater or equal to P2, and then it's the probability of a type 2 error if P1 is less than P2. So the risk is nothing but the probabilities of type 1 or type 2 error. And if you look at the base risk in that case, then that's going to be the average of this risk function with respect to the prior that you had put on P1 and P2. Okay, and it turns out that that is simply the sum of the average probability of type 1 and the average probability of a type 2 error. So those are the elements in that situation. Here's another problem that to illustrate that. Mitchelson was trying to determine the speed of light. This was an experiment in 1879, okay? And he had 100 observations, a very intricate experiment that he did in the Washington Monument. But these are the data that he was obtaining. That is in 10 to the 6 meter per second, that thing. You notice, of course, that you don't get the same value. The speed of light should be a constant, but you don't get the same value, because when you take your observation, noise comes into the observations. Okay, so you want to denoise to do that. That is the data that he has, and this is the histogram of these 100 data points. And I think the center there is about 299.9 times 10 to the 6 meter per second. That's the speed of light is very close to that. But you have this variability, and that's because of the noise in the measurement. Okay. Now, how do you put this in this framework? So you could take the loss function here as simply the square difference between the action and then the speed of light. In the action is simply a real number. Okay. There's the parameter, the theta, will contain two things: the speed of light, and then the standard deviation associated with the error contamination. You could put a prior on theta, which could be normal, that's your prior belief. And then the observations will be x1 up to x of 100, which will be equal to the speed of light plus an error contamination. That's why here you have this variability. That's because of these epsilon i's. And you typically would assume that that error contamination has mean 0 in standard deviation sigma. And then that is the sigma that goes in there. Most of the time, you assume that that's normal, but you are not required to put a normal distribution in that. So the data that you see then will be the observations. And what you would like to do is to come up with a decision function that depends on x1, x2, up to x of 100, which will give you a real number, which will be your action. Okay? And when you look at the risk function for this decision function, you get a very interesting form. It is what you call as the bias or the variance of the decision function plus the square of the bias. The bias is the difference between the truth in the average value of your estimate. So you have heard the bias plus the variance plus the bias square. That is the risk function. And what you would like to do is to look for a delta that will make this small. Okay, so that's the game that you have to play. And I put here just a simple one. I said, what if you consider linear combinations of the observations? Okay, so just another kind of a linear combination of the 100 observations. What's the best one? Then you could theoretically calculate the risk for this. And when you do that, a very simple calculation, it gives you this risk function. And then these are the coefficients. Okay, so if you want this to be minimized, what you need to do is to take bi to be 1 over n. And consequently, what will happen then is that the best decision function among these linear combinations of the observations is nothing but the sample mean that most of us are using or have seen. Okay, so the sample mean is the best among the linear combinations of these type. Okay. Now, I wanted to mention a little bit about bias invariance. Okay. So when you have an unbiased decision function, what it means is that on the average, you're on target. So the target's the red one, and then these are the possible outcomes of your decision function. And on the average, if it is equal to that red one, then you have unbiased one. Biased, on the other hand, is that you're off target. This is a biased decision function. You're not hitting on the average target. You're kind of biased. Okay, that's why I call it bias. And then you also have the big variance. Big variance has lots of spread, okay, as compared to small variance. Small variance will have this. And typically what we would like is a decision function that is of this form, unbiased, small variance. But sometimes you could allow for bias. If you could correct for the bias here, and then you have a small variability, that might be better off. Okay, but you would like to be in this form here. You don't want this. Okay, your decision function should not be in this category. It should be on these two. Either this is the best, or this one here. If you could control for that bias. So that's the idea behind what we call as the bias-variance trade-off, which is very important in machine learning, data science, artificial intelligence, in all of statistics. Okay. So the next question that I wanted to ask is, what's the basis of deciding on your decision function? The first one is to try to minimize the risk, okay? But when you want to do that, you might need to restrict your class of decision functions in order for a minimizer to exist. I'll illustrate. In possible ways of restricting is that you could impose the unbiasedness restriction, the one that I just showed, or you could have what we call as group invariance or symmetry considerations. Okay, I will not mention this anymore because that's a more complicated notion. Or you could put a maximum of the risk over a certain region of the truth space. Okay, then if you could then minimize on those restrictions, then you have found a good decision function. And this idea in pictures. Okay, let's say that you have a decision function delta star, delta 1, delta 2, and delta 3. And then these are the risk function. You notice that delta star has a risk function that is smaller than all the others. In that situation, you would say delta star is what I'm looking for. Okay, and if you properly restrict your decision function like the linear combination, you might be able to obtain the best one. Okay, and then that's delta star there. Okay, now, so I put this slide here because it's kind of interesting. You might ask, is the sample mean always the best one? Okay, because that's what we use a lot in everything that we do teach our basic statistics students. And the answer is no. It depends. If you have a uniform population, for instance, it turns out that you could use what you call as the sample mid-range, which is the average value of the two extreme values. And if you use the sample mid-range, it's a lot better than the sample mean. So this is a simulation of the sample mean in the sample mid-range under a uniform population. In the sample mid-range is much, much better than the sample mean. So if you use the sample mean to try to estimate the center, you're sacrificing a lot of efficiency. Okay, you have to use something else. So the point that I wanted here is that it's not always the sample mean that is best for estimating the center of your population. Okay, it depends on the population that you're considering. Oops. Okay, now, so the question that comes up then here is, how do we know if we actually got the best decision function? How do we do that? Okay, so here's a simple one. Okay, if a decision function achieves the lower bound of risks for its theta, okay, then it's got to be the best one because it is achieving the lowest bound. And what happens that we have this Cramer-Rao information inequality? Rao is the one that I mentioned in the beginning, by the way, which says the following, that if you have an unbiased estimator or decision function for tau theta, means the average of delta is equal to tau theta, the variance of this delta x is bounded below by this, what you call as the Cramer-Rao lower bound, and that is given by this. And this is the information, the feature information, okay? So if you could find a decision function that actually achieves this variance, then you know that that's the best one because you have achieved the lowest possibility. That's one possibility in which you could determine the best one. Okay, well, that's what we call as the Kramer raw information inequality. Now, another way of being certain, though, that you get the best one is this. Imagine that there is a function x, say s of x, we call that as a sufficient statistic, such that for every decision function delta x, there is another one that depends on sx that has the same average value, and such that the risk of this is smaller than or equal to the risk of delta. Okay? Now, imagine further that there is only one such delta star x, sx. Then you know in that case that that's got to be the best one. And Xuen, I think, is in the audience. I always joke when he was in my class that if Xuen is the only man in town, all the girls will say Xuen is the handsomest of them all because there's only one. Okay, there's only one to compare, and that is that one. And this is the situation here. If there's only one decision function that depends on Sx, then it's got to be the best one because you give me any other, I could improve by using this. Okay, and that's the essence of what we call as the Rao-Blackwell theorem. Again, Rao, that one that I mentioned in the very beginning, is an originator of this theorem, and then Diliman theorem, and it is related to what we call a sufficient incomplete statistics. Okay, so two ways in which you could determine that you have actually the best one, and these are very big theorems in mathematical statistics. It's kind of difficult to understand in the beginning, but the essence of that is what I just mentioned to you. Okay, now the other possibility that I mentioned earlier is that so this is the truth space, and then there might be a region there that you say, I don't care here, I simply want to bound the rest. So you could bound by alpha, okay, on this part. And then what you want to do is to minimize on the other side. Okay, so in this situation, the delta star will be the best one because I bounded it here, but then it has the lowest risk on the other side. Okay, in that situation, you would say that delta star is the best decision function too. And this is the situation in hypothesis testing. In hypothesis testing, you subdivide the truth space into two parts, okay? And then you're deciding between this part or this part, and then you have the decision function. Usually you would specify what we call as the level of significance, the alpha, okay, that you have. And then what you have there is that if you have this situation and you're using the zero and loss function, among the decision functions that bounds on that theta zero, the risk, the best one is given by this. This is what you call as the likelihood ratio, and that's given by this function, okay? And this actually is the theory behind the t-test, the analysis of variance, the chi-square that maybe some of you had used these procedures. This is the whole theory behind that, okay? And this is what you call as the Niemann person theory. Okay, I think it must have been on the other slide. Okay, but this is the best type of decision function. Now, the other possibility is you say, could we have a global criteria for deciding on the decision function? And there are two ways of doing that. One of them is what you call as the minimax principle. And the idea behind the minimax principle is you safeguard against the worst case scenario. So what you do is you maximize over theta, okay, for a given delta, and then you look for that delta that has the smallest maximum, okay? And that's pictured here. So this is the minimax principle. You have the decision functions, you have the risks, you look for the largest value for each of them, and then you look for the one that has the smallest maximum risk. If you could find that, that is what you call as your minimax decision rule. In the idea there is that you want to safeguard the worst possible case. There you wanted to safeguard against an opponent that is trying to beat you, okay? So like in a game. So while the other principle that we use, if you wanted a global criteria, is to use the Bayes principle. In that case, you try to minimize the Bayes risk. Okay. In that case, you have the Bayes risk. Look for the delta that has the smallest possible Bayes risk. Okay. In that case, that will be the Bayes decision function. And that is kind of pictured here. You have two risks. Okay. I simply put a uniform prior. So you look at the areas under these two risks. Whoever has the smaller one will be the better one. And then if you could look for that delta star that has the smallest Bayes risk among all of them, that is your Bayes decision function. And that will be what you'll be using. So there are several ways to decide on what decision function to use, either using a global criteria or restricting the decision functions or restricting on a certain portion of the sample space. Okay. Now, here's the Bayes updating. Okay. So if you have the prior knowledge, pi theta, and then you observe data, you could update your knowledge by using Bayes theorem. This is what you call a Bayes theorem. What this does is it combines your prior information with what the data is telling you according to this. Okay, and so it's a hybridizing of the initial knowledge in the knowledge that you obtain from your data. It is what you call as the posterior knowledge of data given the data X. Okay, and it turns out that if you have this posterior distribution, you could obtain the Bayes decision function by simply minimizing this. Okay, so for a given data, you use that. That's that one. Take the average value of the loss. Look for the action that will minimize this posterior Bayes risk. That is your Bayes decision function. Very simple formula, very simple prescription to find the best Bayes decision function. But you must be able to do this. In the olden days, the difficulty is finding this posterior one, because sometimes it's difficult. But with computing technology, it's very easy now to do this computationally, so you are able to determine the Bayes decision function. Okay? And I mentioned here, how does one obtain priors? Now, and that's a subjective thing. That's what you know about that parameter. So two people, Raymond here, could have a different prior, and then K could have a different prior, because those are your subjective opinions or your prior knowledge about what you're studying. Okay, and the problem here is that different people could have different priors, and there's the issue of subjectivity. Okay, what happens though is that even if two people have different priors, if you keep observing more and more data, that posterior distribution will converge to the truth. Okay, so it doesn't matter in the beginning, but as you keep getting data, it will actually converge to the truth. And there's the notion too, what you call as the least informative or the least favorable priors. Okay, and if you have a flip of a coin, and then theta is the probability of head, your least informative prior there is the one that's flat on theta. It has the least information. And it turns out usually that the Bayes decision function under the least informative prior generally will coincide with the minimax decision function. So it looks that this is difficult to obtain, but if you could obtain the least favorable prior, you can obtain the Bayes decision function. It turns out to be the minimax decision function. And there's some intuition there, but I don't have time to do that. I wanted to mention though that Bayes updating allows for sequential learning, iterative process of experimentation, updating, and experimentation. And this is the idea behind the sequential updating. Again, this is the truth. You have the prior knowledge. You do an experiment that is informative. You get the data, okay? And then when you observe the data, you update your prior, you obtain a new distribution, which is the posterior, which now becomes your prior. And then you do another experiment. And you cycle through this. And as I keep doing this, your posterior becomes better and better, and it will converge to the truth. So the Bayes formulation actually, in a sequential way, will lead you to the truth, provided that you you stick with the posterior as your new prior. If you keep changing your prior, maybe like what is happening with the government, then you will never reach the truth. But if you do the sequential updating, this will converge to what the truth is. It will converge to what you call as a degenerate distribution. Okay, so that's the idea behind Bayes updating or sequential updating. Now let's see. I think I run out of time here. So I just wanted to kind of mention this. This is similar to the previous problem that I mentioned earlier, deciding between two groups. Okay, so and what you have is that two distributions. These are actually binomials, and then you have a likelihood ratio. Okay, that's the one that I was mentioning earlier. And then this is the decision rule that you usually use, okay? And then I put power here, which is the reverse of the opposite of the risk. And you'd like the power to be high, and then the probability of type 1 error to be low. And then you're deciding on the cutoff value. And I say here, no free lunch, because if you sacrifice one, then the other one will go up. If you sacrifice the other, then the other one goes up, okay? And this is the significance approach that I was mentioning in the beginning, Fisher's approach, and you obtain here what you call as the p-value, which is the probability of observing more extreme cases. Here it's very small if you see at 22. And then this the Diliman person Wald approach. Okay, I don't have the time to discuss, but I have this long paper. You could look at that with regards to using this framework. And then this is the Niemann-Person theorem that gives you the best possible decision function in this setting. Okay, this is actually the theory behind the one that I mentioned earlier. Okay, so in the implementation, so too much information here. And then this is the posterior updating. Depending on the number of red balls that you obtain, you could obtain the posterior distribution probability. And then you notice that it depends on where you are. It gives you a very good posterior updating in that case. That's using the Bayes theorem. Okay. Now, I just wanted to mention to end here the COVID-19 application that we had. This is for the US data. And this is the data that we had until September 13. Okay. This is the reported daily deaths from December 31 up to September 13. Okay. Those are the daily deaths in the US. These are cases. And what you would like to do is to predict the number of deaths, cumulative as well as daily. This is a model that we had using that framework, okay? And the paper is in the archive, so we deposit it there. And then this is the daily predictions. Okay, the black ones here are the observed ones. The red ones here were the observed ones after this cutoff. We use the data to predict this. You notice that we're kind of within the window of prediction. This is what you call as the confidence band. And we are covering the uncertainty in that situation, except for these two. And these 2 points here were adjusted values by New York and New Jersey. So the model that we had looks quite okay in terms of predicting the number of deaths. And then this is the prediction for the cumulative deaths for October 1, okay? The red ones are the observed values after the data that we used. So you notice that it's tracking it well, and then this is what you call as the cone of uncertainty. Okay, as you go further away, you are more uncertain, but this is what you call as the confidence bound or the confidence interval or prediction interval. And the paper here actually is in Kim Lieberman, Lotta George, I think, is in the audience. Then I'm not sure Ben in Taihu. Okay, but we put this in the archive last August. Okay, so we still have to make some changes in the manuscript before submission. But I know this is keeping track. In the prediction, using data until 9/13 for the number of deaths on October 1 is 203,000. On September 1, we had 183,000. Actually, the one using 9/13 is this one. Okay, and you notice that when we use more data, then the cone of uncertainty becomes narrower because we are more certain. And so the prediction for October 1 is 207,361 now. And this is the cone of uncertainty. But in some sense, this is an application of this kind of theory that we had developed. Okay. And I think this is the last slide here. I just mentioned that all of these are related to data science type things. Okay. A lot of the theory behind data science are actually based on these theories in mathematical statistics. I leave you with a food for thought here, because in data science, you typically have very many features. But I ask here, is it better to keep gathering many features? Does it really improve your seeking of your knowledge? Okay, what are the consequences of using features that are not important? What are the consequences of not including features that are actually important? And the key to the answer to this is that bias-variance trade-off. It is not worthwhile to just keep getting data or features. It might not help you in the end. Okay, but those are topics that are very important in the foundation of data science methods. Okay, I think this is my last one. Big thanks to Kay and to Raymond for organizing these, to PAASE for facilitating these webinars and for the scholar discussions. My current and former graduate students always makes me work harder to understand things. The Department of Statistics, NIH, and then the National Science Foundation. And of course, my wife and my little dog, because they always help me with a lot of this. Okay, so I thought I'll put this slide here. I saw this on Facebook the other day. You might think that Facebook is just full of fake news, but sometimes you get a gem. And I thought this was a nice gem. Okay, it's a doodle on a Facebook post that I saw, and it's about science and the points that we should make science be more accessible to the public. And this is the essence of the thing there. So it's a nice little thing. But sorry, I exceeded time here. I put a lot of things there, but I wanted to be as complete as possible in terms of introducing some of the principles that we have. So, Ray,
Well, thanks very much, Edsel.
yeah, sorry again, I exceeded time.
That's all right. Kay has had to leave because she's giving her own talk at 9 a.m.
She mentioned that.
I'll be taking over from here, and my colleague Aris Obando, who's also a PAASE member, will be helping out with the YouTube stream, because it takes two men to do the work of one smart woman. So I'll go through the
correct. Yeah,
it is correct. Yeah. So we'll go through the first few questions. Number one is from Angie Lau of De La Salle University. Instead of searching for truth, can similar approach be applied to detect lie or rampant fake news, for example?
Well, you just, that's a good point. Yeah, so, so of course, lying or fake news is the opposite of truth, isn't it? So, no, that's a good point though, because the data that we are seeing, okay, is of course reflecting what the truth is. Okay, so in that situation, I think if you are looking for fake news, you have to create a model, a probabilistic model for what fake news model is. Okay, like because the whole idea is that the probability function distribution that we are using is based on the truth, the parameters about the truth. So if you flip that, you say, I have a parameter theta that represents fake news. Then you could create a model based on that parameter, and then the data that you are seeing is being compared to that distribution of fake news. So in a sense, in principle, it does. Yeah, you could. Yeah, but you just have to alter the model. Now, the problem, of course, in science is this is what we are interested with. When you do an experiment, your experiment reflects what you are trying to discover. Okay, so yeah, interesting question. Yeah. Potentially, yes. Yeah.
Thank you for that. We'll move on to the next question. This one is from Rafi Cabredo. also of De La Salle University. How should we handle truth when it changes over time or specific to individuals? For example, the definition of beauty, which was different in the 18th century from how it is now. In the case of art, music, which varies with people's tastes. And would big data help define such abstract or subjective concepts?
Well, in that situation, your parameter, the data that we had earlier, will now be dependent on time. Okay, so you could have also the situation where the parameter actually is time dependent. Maybe that's the case in the stock market actually. If you monitor, say, the Apple share price, the truth there is it could actually be changing. So you have a time dependent truth. Okay, and again now. In that situation, you have to use a stochastic process model because now you have to tie it with the time axis. Okay, so at any given time, the truth had changed, and you are reflecting that. Now, of course, one of the questions there maybe is how do we describe the changes in the truth as time passes by? And that's a stochastic process problem, but it's still the same framework. You could put it in this context, except that your data is now dependent on time. And we have models for that too. Yeah, and Markov chain models, or actually even in the COVID thing, you might say, what's the infection rate? What's the R naught in the COVID problem? That changes over time too, because that depends on the interventions that the government or the people are doing. So maybe in the beginning, it was quite high, so the theta is higher, but then it changes, it decreases as time passes by. So you want to adjust for the effect of time on the truth parameter in that situation. But the principle is the same. On any given time, you could get an experiment, you could get data, and you could estimate the value of the parameter at that time. But as time passes by, things change. Yeah. But that's an interesting problem. The weather, climate, for instance, is another situation where things depends on time. Okay. So that's a situation where which might be describing the setting that that you have there. Beauty, of course, is changing. The notion of beauty is changing. I think there has been some research on that. Where remember, I'm not sure if you had seen this news about the golden ratio. That if a face of a person satisfies the golden ratio, okay, then that's the definition of beauty, because the Greek in Greek mythology, a lot of the architecture satisfies this. So there has been some sociological studies on this, and it turns out that in Polynesia, that is not the case. That beauty is different from the golden ratio. So that's one situation where the definition of truth is different. Okay, so of course in science, we are usually looking for the absolute truths or the probabilistic truths, but they could still be changing over time as well. Good question. Yeah.
All right, thank you for that. Now our next question is from Vince Daria, who sends greetings from down under.
Yep.
How do you deal with outliers that can't be explained and reduce the certainty?
A good question. Yeah. Now there are two types of outliers. Okay. There are outliers that are actually valid outliers. They could be outliers simply because the distribution that you're dealing with is heavy tail. Like if you have a Cauchy distribution. Cauchy distribution has a wider tail compared to the normal. And it doesn't actually have a mean in a variance. But if you take observations from this, once in a while you get very large values. Those are valid observations. Okay, those are, and you should not be throwing them out. But there are outliers on the other hand that are simply because of measurement error or something was done. Like if you look at that data that I was showing here, this one here, these are obvious outliers. And if you see that type of outlier, say, what happened there? There could be an explanation. In the explanation in this particular case is that adjustments were done in New York and New Jersey. I think they added something like 3,000 deaths on this one day. And then they added 2,700 deaths on this one day. And then notice that the method that we had, which still utilized this observation, put them outside of the prediction region. So, but the procedure actually did not eliminate this data. It used that, but it points out that something's really wrong with this. In the reason for that is this. Now, in the case of measurement error, okay, I'll tell you a situation about this, which reflects what could happen. My wife will kill me after this talk, so despite the last time that you'll see me, okay. When I put gas in my car, I always record the mileage in the amount of gas that I put. Okay, typical statistician. And my daughters are really ashamed of me. Okay, when my daughters were in the car, they would snap their heads under the chair because somebody might see them. Their dad is recording this mileage every time. So I have a nice notebook. Actually, some of the data actually was just in a paper in JASA, in the Journal of the American Statistical Association. But one day, I see this data. I was analyzing this data bins. And I said, this couldn't be. This data is really just out of context, okay? So one of the data out of 200 observations. And then I look at this data. I said, who wrote this, okay? So, and it turns out that it was Marge who wrote this data pointer. And I don't know what happened. I think she forgot to record after she put gas into the car and then realized that she had forgotten. So she just put a random number in this data set. And of course it popped out. And I said, you cannot do this. You're very untrustworthy. You couldn't be a statistician in this case. So that's the situation where you have what you call as measurement error, or when you have noisy data because your wife put a random number into the data set. So be very careful with that. It could happen with graduate students, with students. The students were talking on the phone, and then he was supposed to be observing a test tube, and then suddenly the observation is gone, and they said, oh, let me just put a number here. And statistics don't lie in that case, because when you look at the totality of the observations, those types of observations that are fake observations will actually show up. Okay, so and then there you have to remove those data points because they do not contain information in that case. Yeah, so but that's a good point. You have to be careful. Don't just throw out observations because those observations could actually contain information. You might have to downweight them in the analysis, but throwing them out could easily bias your results in that situation. So, but that's a good point. That's outliers is a pest in the context of statistical inference. And we always try to be careful about that, but you have to examine it.
I have to defend myself. Actually, there was one point that actually was an outlier. So this is one where we were still in Michigan, where actually it was a time when there was a blizzard and the car was driving. It thought that the car was driving so slowly, but we were actually pushing it up the hill because it kept sliding down in the snow. And the mileage for that particular incident, we were actually able to point out came from the time that we were pushing the car and it was going up and down the hill and so on and so forth. So
no, that was an explainable one.
Yeah.
Outline.
I don't remember now.
Data,
Yeah.
that
I
measurement
do forget. So sometimes I write random numbers. I thought I would not get caught.
Then since Marge came in there, so I was serving as her statistician in one of her experiments. Okay, and one time she came to me and she said, the results are not significant. Okay, but it was very close to being significant. And she said, whispering and wives could be a little bit persuasive. She said, could I just remove this observation? And if you remove this observation, things will become significant. And I said, you couldn't bribe your husband. So.
This was actually an experiment where we had one mouse that we predicted was going to die from the chemotherapy. So the mice looked very sorry looking. For all intents and purposes, had lost weight.
No.
It just would not die. so everybody was making sure I didn't go to the mouse house to kill the mouse. But yeah, the perils of mouse experiments.
Yeah, those are interesting situations. Yeah. So,
Okay, our next question is from Royet Posadas. It's a 4-part question. In a set of groups, say you have 18 groups, 2 of them are non-normally distributed. Is it still valid to use parametric tests? So that's part 1 of our string of questions.
Okay, not that one. You have to be careful there, yeah, because this is one of the things that we emphasize as statisticians. Statistical procedures, their validity depends a lot on the assumptions that are imposed. Like for the t-test, for instance, the t-test is, especially for small samples, the normality assumption is very critical. If you don't have that normality, you might put a 5% level of significance, but that's not what you are achieving. So in that situation, it might be better to use non-parametric methods because non-parametric methods are robust for assumptions. They're typically less powerful, okay, but they are robust, they're valid in that case. But if you use a parametric test and then the assumptions are actually not satisfied, you are deceiving yourself in that situation. So now if the sample size is large, like you're using ANOVA or t-test, even if you don't have normality, things are acceptable in that situation. But for small sample sizes, you need to be very careful, and you might want to do a non-parametric test to do that, and maybe compare it with a parametric one. And if they lead to 2 different answers, you have to stick with the non-parametric one because that's the more valid procedure. An example of a non-parametric procedure is simply using the sign of the values, or it could be using the rankings. Okay, in that situation, you have a valid procedure because it covers all distributions, but you get less sensitivity in that situation, but you have a valid one. Yeah. So.
Right, thanks for that, Edsel. The next question from the same person is, which is more appropriate to test for equal variances, Bartlett's test or Levene's test?
I can't remember now. Yeah, those are both tests, isn't it? I usually use Bartlett, but I know that there's a difference between the 2. Okay, so I need to check that. I haven't used it for quite some time now, so I don't have automatically in my mind which one is the better one. But I've used both of them. Haven't used them for quite some time now. Yeah.
And maybe I'll throw in the last 2 questions because they seem to be related. Which data transformation technique is the most powerful? And when transformed data is still non-normally distributed, should I still use parametric tests?
Yeah, again, that's the issue there. But should you simply use non-parametric procedures in that case? Of course, there are many data transformations. The Box-Cox transformation is one possibility. But here's the problem that you need to be careful about. When you make the transformation, let's say the Box-Cox is an exponential transformation. You say x to the alpha. When you choose the alpha that you have, you typically use the data to choose that alpha. Now, when you use the data, and then you use the data again for testing, you are double dipping. And when you double dip in the data, that could have bad consequences because they're related. So yeah, you need to be very careful there. Now, if you use a non-parametric procedure, on the other hand, you don't have to do that double dipping. So, but we use that, you just have to be careful in adjusting for the transformation. Now, sometimes there's transformation like the log transformation or the square root transformation, where you don't have to estimate the parameter of the transformation. In that case, that could be okay. But if you still do not have that kind of normality, then you might as well make use of the non-parametric procedure. I think it is better to be safe than trying to force things there. Yeah. And a lot of data science methods actually are more non-parametric in nature as compared to being parametric. Yeah. But some people there, George, for instance, could answer the issues there. Yeah. So George Luta is from Georgetown, and he has more experience on those types of things. But those are issues. I think double dipping or triple dipping is something that people don't realize too much. But when you do those double dipping or triple dipping, they could be very, very dangerous because you might lose information immediately because of the transformation that you have done. In fact, in some papers that I published, I demonstrated this negative impact of double dipping in the context of model validation. I mean, very interesting papers. I think it is one with Immaculada Aban, who might be here. Yeah, so but it was part of her dissertation in the 1990s, where we demonstrated that if you do this double dipping, information could suddenly disappear on you, and what you might be using doesn't have any information when you are trying to do the model validation. It's complicated issues, but those are issues that are studied well, yeah, and has big consequences.
Now, if Joel is still in the room, I think he wants to ask his question via audio. Joel, are you still with us?
I think he left. Joel already left the room.
All right, Aris, do we have any questions from the YouTube channel?
From the YouTube channel, no questions so far.
All right,
but
thanks.
We can proceed with the questions from the chat box.
Okay, so the next one, Zita Albasaya is asking, in machine learning.
I think Zita was my student when she was an undergraduate student.
Oh, okay, so it's all in the family. Yeah. In machine learning,
all in the family, yeah.
Most of the time, the assumptions of regression are violated. How far can we allow this kind of violation?
Machine learning methods are quite interesting because the way we usually tune things is we typically split the data into two parts: the training and the test data. So you kind of separate things, and then so you do the training, and then you test it, and you say what's the appropriate smoothing parameter, for instance. Okay, so it's actually kind of non-parametric in that situation. Of course, a lot of times in machine learning, that's actually related to that question that I was asking here in the end. What happens if you don't use features that you should be using in the regression model? What's the consequence of that? And the consequence of that is that you will get bias, a lot of bias possibly. If you don't use features that are supposed to be there, then you will get bias. But what happens if you use features that are actually not important? It also has a consequence. And the consequence of that is that it will increase your variance. You get less precision. Okay, so there's no free lunch. Okay, so in the sense that put features there that are not important for the model, then that will just blow up your variance. Why? Because you're estimating more parameters that are actually zeros. Okay, so that's when you usually do regularization to correct for that. On the other hand, if you don't use features that are supposed to be there, okay, then you will be off target. So there's a question there of balancing, and that's where the training test approach comes in, because what you're trying to do there is to determine what variables should go in there, and then you train, and then you do that testing to see how good it is for different values of the smoothing parameter. And it's a little bit different from what we usually do in statistics, but this is now the approach that we do in data science or machine learning, where we have the splitting of the data, and then the cross-validation, for instance, comes in, and so on and so forth. But I'm not sure if Sita was asking if the model was supposed to be non-linear, and then somebody's putting linear models. You should be able to detect if the assumed model is actually off through the residual analysis. Yeah. But there's
Okay.
there's still a lot of foundational issues in data science. In fact, in the National Science Foundation, this is one of the big questions, big projects that we are seeking proposals, foundational issues of data science methods. And I think statisticians could have a big say on this, because the the analytical properties of these methods could only be examined mathematically. You couldn't examine their properties through just computation. Yeah, there should be some foundational mathematical analysis of these procedures, and that is currently what is missing, I think, in a lot of the machine learning, data science methods, deep learning, neural nets, and it's a big area of research.
All right. Thank you for that, Edsel. The next question is from JJ Joaquin of De La Salle University, who first says, thanks for an excellent and clear talk. And he has two questions. First, you've defined the probability space in terms of truth space, but this does not cohere with the standard Kolmogorov definition in terms of a possibility space. I wonder if the definition is grounded in a more objective or realist conception of the nature of probability.
No, it's actually Kolmogorov's. In Kolmogorov Kolmogorov simply deals with a probability measure. Okay, so in this case, Kolmogorov was simply dealing with how do you assign probabilities to subsets of the sample space. Okay, if you have to assign one, and what are the properties of the probability function? Okay, so so he puts it in an axiomatic way, where he starts with 3 axioms or 4 axioms. That the probability of the whole sample space should be 1, that the probability of any event should be positive or non-negative, and then you have what you call as countable additivity, that if you have a sequence of disjoint events, then the probability of the union of those events is the sum of their individual probabilities. Those are the axioms of Kolmogorov, and it pertains to one probability function. Now, when we deal with statistics, though, we are dealing with a family of probability functions. Okay, so for every theta here, that will coincide with a p theta. That's the probability function. But whatever that theta is, that p theta must satisfy Kolmogorov's axioms. Okay, so consider you have now a family of probability functions or distributions or measures. And then basically you're trying to determine that theta that corresponds to the truth. So you have these many probability measures. Those are what we call as the theories. You get data, and you say, what's the truth? What is the probability measure that is governing that? So that's associated with one theta. So p theta is one probability measure, or you could also think about it this way. But they all must satisfy the Kolmogorov axioms, in the sense that they must satisfy all the consequences of Kolmogorov's axioms. Now, Kolmogorov doesn't say anything about how you obtain your probabilities. Okay, it could be a frequentist justification, it could be a theoretical justification, or it could be a subjective justification of how you assign probabilities. Whatever your method of assignment, though, they must be consistent in the sense of satisfying the 3 axioms. So as long as you're consistent, it doesn't matter. It could be subjective way, or it could be a frequentist manner of assigning probabilities, or it could be a theoretical manner. But they all must satisfy Kolmogorov's axioms of probabilities. Otherwise, everything breaks down. The thing in statistics that you have a family of these probability measures, not only one. Okay, as compared to the probabilistic Kolmogorov axioms, you only have one probability measure. In statistics, you now have this family of probability measures. You want to pick the one that is governing the data that you are seeing. So that's the thing there. So in statistics, it's a bigger one, but each of them must satisfy the Kolmogorov condition.
Right, and the second part of JJ's question, is you seem to shift to a more subjective definition of probability in the decision theoretic definitions. Is there a bridging principle that links the objective and subjective probabilities?
The subjective probability here, okay? So this one is an objective part, okay? The probability measure that you have there will be an objective part, okay? The subjective probability is the prior knowledge that we put there, okay? Because the prior knowledge, as we were saying, if I give you a coin, I say, what do you think? Is this a fair coin? If I ask Raymond, being an engineer, he say, oh, this couldn't be completely symmetric. He might say, this is not fair. So you have your kind of prior knowledge about the fairness of this coin. Somebody on the other hand, it could be, say, Aristotle. Okay, I ask him about this coin. Aristotle is more a philosopher like Aristotle. He might say, oh, that's got to be a fair coin. I would put a prior of 50-50 in that situation. So now that's the subjective part. Okay, the prior knowledge that we put about the truth is actually subjective, and they could be different for different people. But for an experiment, on the other hand, whatever experiment you are performing, that will lead to a specific distribution. It depends, of course, on the experiment that you're doing. If I flip a coin 30 times and I count the number of heads, then that will lead to a binomial distribution. On the other hand, if I keep flipping the coin until I obtain 10 heads, that will give me a negative binomial distribution. So that will change the thing, but that's an objective probability. So the subjectivity is on this prior knowledge. And then when we get into that Bayesian approach of learning, which is this, okay? So this is the subjective part, okay? But the experiment that we're doing will be an objective experiment that will lead to information, to a data that is informative. But when we update the subjective knowledge, okay, with this data, then of course this is still subjective in some sense, but it incorporates the objective information that we are getting from the experiment. So this will now become your new prior. Then you do your experiment, another experiment, or another person does another experiment. But now it is prior. And so this cycles through. So this sequence of posterior probabilities, in some sense, are actually subjective knowledge that emanates from the initial knowledge that we had imposed. But it is getting updated and updated by the data that we are getting from this sequence of experiments that people are doing. And that's the one that will converge to a degenerate distribution on the truth. Okay, whether theta zero or the probability measure that is governing the thing, it will converge. So, but this is subjective, there's the part that is objective. That's a very good question. There's always that difference between subjectivity and objective things there. But knowledge is subjective, or the knowledge that we think we know is actually subjective.
All right, I think JJ may have some further comments which are better discussed via email because they may take some time. But we'll take our last question, which is from Giselle. Let me see, let me find that question in the chat box. Okay. Edsel, excellent, exciting sharing of your expertise. Thanks. What is your conclusion on the efficacy of HCQ based on the randomized based, what is that?
There were
trials, randomized trials.
Yeah, there were 3 trials actually or 3 papers that were published about this. And I think the 3 papers which were kind of controversial, they didn't find significant results, but then when they made their conclusion, they concluded that hydroxychloroquine is not effective. But from a statistical point of view, you couldn't really make that conclusion that they are not effective. What it is simply telling us that the data that we had so far seen is not sufficient to conclude that they are actually effective. But I think, I don't know how they concluded that or how the reviewers let it go. But those are the conclusions of that thing. But I think that's not the right conclusion from a statistical point of view. And let me explain this a little bit, okay? So when you have 2 hypotheses, one is the null, and then the other is the alternative. The null hypothesis typically coincides with the status quo. And typically that will be that hydroxychloroquine is not better than placebo. The alternative, on the other hand, is the research hypothesis, and then that is that hydroxychloroquine is actually effective. Okay. When we do a hypothesis test, a statistical test or a decision function, we control for the type 1 error probability. That's when you set, say, 0.05 as the maximum probability of a type 1 error. When you do that, you don't have control on your power or the probability of a type 2 error unless you have decided properly in your sample size. Okay? So consequently, when you reject the null hypothesis based on your data, you could conclude that the alternative is right because you have control on the type 1 error probability. But if you do not reject the null hypothesis, you don't know anything about the chances that you have committed a type 2 error. In that situation, then, you couldn't conclude that the null hypothesis is correct. And this is the situation, this hydroxychloroquine. I'm not a supporter, by the way, of either one. I wanted to see what is the truth in this case. But the 3 papers that came out, which were kind of controversial in the past 2 months, or past month, I think, their conclusion was a little bit wrong from a statistical point of view, because they were saying that they were not able to reject the null hypothesis. So they then concluded that hydroxychloroquine is not effective. That's not the right conclusion. You could only say that the data does not yet support the potential conclusion that it is actually effective. Yeah, so it's kind of inconclusive at this point. So, but I think lots of trials are being done. They will come to a definitive conclusion. Data is coming and the updating is happening. So we will eventually find what the truth is in that. Of course, it would not matter if you get a vaccine. Okay, the vaccine is what we need. Otherwise, we'll never reach our normal way of life without a vaccine. But at the same time, the vaccine trials should be done properly, because if they are not done properly, then the trust of people on the efficacy of this vaccine will also go down. And if I don't trust that the vaccine was properly studied, I might not take the vaccine. Okay, so those are important considerations. That's why we need to put the trust on science at a higher level again. It's an objective kind of science that we want, so it's very important.
I'll just end by reading a comment and message from PAASE President Giselle Concepcion. Edsel, we always thank BASE and you as scientists for moving evolutionary biology, phylogenetic science forward. In regard to chemistry and biochemistry, small molecule science, either we have the right structure or not definitively. And when we deal with complex biomolecular structures, we need to measure the probability of correctness of 3D structure unfolding. It all depends on the high or low resolution measurements from instrumentation, and complexity of structure complexity is what we handle well using stats. Now, she also is suggesting perhaps we can ask Kay to invite you again to give a talk at your convenience on the controversial HCQ results. But
I might not be the right person for that.
All right. But well, that's about all we have time for this morning. I just want to end, as Kay normally would, by announcing next week's talk. So if Edsel, if you would please unshare your screen,
yeah.
So I can share the file that I'm supposed to show next. All right. So next week's talk is next week. We're going to have a talk at this same time by Dr. Cherry Murray, professor of physics at the University of Arizona. And the title of the talk is the UN Sustainable Development Goals and the Pandemic. And finally, of course, for those of you who are interested in past webinars, These are held every Friday at the same time, and past webinars are on record. There's a YouTube channel where you can actually view whenever it's convenient for you, the 20 other lectures that we've had. So thank you once again, and thanks Edsel and Marge as well for your anecdotes about marital statistics in the blizzard. Thank you everyone for staying with us and for attending this event, and keep safe in the pandemic, everyone. Thanks.
Okay, thank you also for everyone that attended. Yeah, thank yours, Shue, I think, Marcos, Tayo Kim is actually there, Chichi's there, my former students. Yeah, thank you very much. Yeah.
Bye.
Bye.
Bye-bye.